Have you ever wondered what happens to a star when it gets too close to the center of our galaxy? Not just close, but dangerously close to something so massive, so powerful, it can bend light and swallow time itself. What if I told you there's a star racing around that invisible monster at speeds so fast, defies our understanding of physics, moving at nearly 8% the speed of light? That star is real, and its name is S62. Welcome to Sleepster, the channel where curiosity comes to rest and wonder whispers you to sleep. Before we begin, tell me, where in the world are you listening from tonight? And what time is it for you right now? Let me know down below. I love seeing how far these sleepy stories travel across this spinning planet we all call home. And let your body soften like stardust. Now, settle in. Take a deep breath. The star that dances with darkness. Because tonight, we're refollowing the trail of the fastest star ever discovered and the black hole that keeps pulling it back. Ready? Let's drift into the cosmic mystery of S62. At the very center of our Milky Way galaxy, hidden behind thick curtains of dust and gas, lies something unimaginably powerful, unimaginably heavy, and almost entirely invisible. It doesn't shine, it doesn't glow, and yet everything near it bends toward its pull. Scientists call it Sagittarius A*, a supermassive black hole, weighing more than 4 million times the mass of our Sun. And so unbelievably close to a black hole, we have to go back. Not just in time, but in distance. Let's take a quiet journey inward, into the Milky Way itself. Every 10 Earth years, it completes one full loop around the black hole. At pericenter, S62 accelerates to its top speed to 8% the speed of light. It is the fastest known natural object orbiting the Milky Way's central black hole, moving so quickly that if you were standing on its surface, the stars would appear stretched, smeared by the effects of relativistic Doppler shift, and time would seem to slow, not just metaphorically, but literally. According to Einstein's theory of general relativity, clocks on S62 would tick more slowly than ours. In fact, each time it swings near the black hole, its experience of time becomes different from the universe around it. This effect is called gravitational time dilation, and it's not a theory anymore. It's a survivor in the most extreme sense of the word, a star that has adapted to orbit a monster and lived to tell the tale. It may be far from Earth, but it offers us something precious, a laboratory to test the deepest truths about the universe. And perhaps even more than that, it offers a kind of quiet metaphor that even near the edge of destruction, something can move with grace, with speed, and with resilience. It's been measured, confirmed, and now we see it in stars like S62, far beyond the reach of our telescopes, but not beyond the reach of our imagination. It reminds us how little we know about the space we live in, and how much beauty there can be in the tension between light and dark. That might sound long, but remember, it's doing this in a region where space is warped, where time slows down, where a single orbit brings it closer to the event horizon, the edge of the black hole, than any other star we've ever observed. These stars are a mystery to astronomers. They're young, far too young to be living so close to a black hole. In theory, the environment near Sagittarius A* should be too violent for star formation. The gravitational tides should tear apart any cloud of gas before it has a chance to collapse and ignite into a star. And yet, here they are. Dozens of stars, including S2, S38, and the speedy S62, all burning brightly in defiance of expectations. During its closest approach, called pericenter, S62 comes within just 16 billion kilometers of the black hole. That is about 3 times the distance between Neptune and the Sun. And while that may sound far to us, it's astonishingly close when you're dealing with something that can erase reality. Picture it from above, a vast spiral of stars, arms curling gracefully like the brushstrokes of a painter, stretching over 100,000 light-years wide. Our solar system lives on the outskirts, a quiet suburb compared to the chaos of the center. But at the core of this spinning galaxy, things are different. Gravity is stronger. Stars are denser. And in that high-stakes region known as the galactic center, stars move not slowly and gently, but fast, erratic, violent. It sits in silent darkness, surrounded by stars that orbit it like moths around a flame. Except this flame doesn't flicker. It devours. The space around it is warped, twisted by gravity so strong it bends light and time itself. Now imagine something trying to orbit this monster. A star. Not just any star, but one that dares to come so close it flirts with the edge of destruction and somehow escapes every time. This is not science fiction. It's real. And this star has a name. Scientists call it S62, and it holds the record as the fastest known star in the entire galaxy. Racing through space at a mind-shattering 24,000 kilometers per second. That's about 53 million miles per hour, or 8% the speed of light. To put that in perspective, if S62 were flying toward Earth from the moon, it would reach us in less than 2 seconds. But to understand how S62 got to be so fast, so bold, this is where S62 lives. Scientists discovered it by peering into the galactic center using one of the most powerful tools ever built, the Very Large Telescope in Chile, equipped with advanced, adaptive optics that cancel out the blur of Earth's atmosphere. For years, they watched a cluster of stars near Sagittarius A*, tracking their orbits like astronomers did in ancient times. Except now they weren't watching planets around its sun. They were watching stars dancing around a black hole. One by one, the orbits revealed something strange. Some of these stars weren't just passing by. They were being whipped around at unimaginable speeds, their paths curving sharply, as if pulled by something heavy and dark. Among them, S62 stood out. Smaller than many of the others, but faster, far, far faster. What's more extraordinary is what happens during that closest approach. But S62 isn't alone. It's part of a strange, stellar family orbiting Sagittarius A*, known as the S-star cluster. So how did they get there? Some scientists believe they were formed farther out and migrated inward through complex gravitational interactions. Others think they may be the result of massive collisions, or even the remnants of disrupted binary systems, where one star gets thrown into the void and the other is captured by the black hole's pull. In fact, S62 may once have been part of a pair. If so, its current speed and orbit are the echo of a cosmic slingshot, a silent reminder that black holes don't just swallow, they also fling. What's equally haunting is that these stars give us a rare chance to test the very nature of space-time. When S62 approaches the black hole, its orbit reveals subtle effects predicted by Einstein's equations, such as Schwarzschild precession, a slow rotation of its orbital path caused by the warping of space itself. In 2020, scientists observed this precession in another S-star, confirming predictions made over a century ago. With S62's faster speed and tighter orbit, future observations could allow even finer measurements, perhaps revealing deviations from current models, hints that something beyond general relativity might be at play. But beyond the math, the data, and the science, there's something deeply poetic about S62. It's a star caught in an endless chase around darkness. Every 10 years, it flies toward the black hole, like Icarus toward the sun, skimming the edge of oblivion, only to swing away again into the cold reaches of space. It is a dance that has likely gone on for millions of years. And in cosmic time, it's still dancing, still orbiting, still keeping a rhythm set by something we cannot see. If you could stand on a platform near Sagittarius A* and watch S62 move, it wouldn't be a gentle, sweeping arc. It would flash past like a bullet. And then, for years, it would drift in the distance, curving back, looping slowly until that next encounter. It's hard to even imagine what the view would look like. Starlight twisted, gravity stretching space like rubber. And at the center, perfect blackness. Not emptiness, not a void, but a place where the known laws of physics break down, where time halts and space folds inward on itself. And yet, S62 survives. As the star continues its orbit through the heart of the galaxy, and so we drift with it now. Into silence, into gravity, into the places where even time begins to slow. Far beyond the soft blue dome of Earth's sky, beyond the frozen silence of Neptune's orbit, and even farther than the distant, dying light of ancient stars in the outer reaches of the Milky Way, there exists a place so powerful, so mysterious, that it bends not only the path of light, but the very structure of time itself. This place is not marked by color, nor by form, but by its absence and emptiness, so profound that it pulls everything inward, toward a center from which nothing can return. According to Einstein's theory of special relativity, time slows down for an object in motion as it approaches the speed of light. That means, for S62, time does not pass in the same way it does for us. If you could ride alongside the star as it slingshots around the black hole, you would experience the passage of time differently than someone standing still on Earth. A few minutes near the black hole might translate to hours or even days elsewhere. Just like Mercury's unusual precession around the Sun helped confirm Einstein's theories within our solar system, S62's strange, shifting orbit known as Schwarzschild precession is, confirming those same ideas at the galactic scale. How did a star like S62 end up so close to a black hole in the first place? Why does it survive each encounter? Others suggest that it was scattered into its current orbit by gravitational interactions with other massive objects in the galactic core. However it arrived, it is now locked in place, a reluctant servant of gravity, destined to repeat its near-death journey over and over until some unseen force or unlucky collision ends the cycle. What fate awaits it over the next 1,000 years or million? The conditions of the galactic core, the nature of black holes themselves, and the many mysteries that still surround high-velocity stars. But for now, just consider this while you lie here listening. A single star is hurtling around the black hole at the center of the galaxy faster than anything you've ever known, brushing against the fabric of space-time itself, surviving on the very edge of darkness. It is, in many ways, a natural laboratory, offering an experimental stage where the universe plays out its most mysterious equations. And we, watching from afar, slowly learn its secrets, as if it's dancing to a rhythm we've only just begun to hear. This is not science fiction. It is science, real and observed. It is here, in the heart of our galaxy, where the rules of nature begin to unravel. It has traveled hundreds of kilometers. It's hard not to marvel at the extremes the universe is capable of producing. It is full of motion, full of conflict and dance, of gravity pulling and time stretching, of stars caught in impossible relationships with darkness. And it reminds us, too, that reality often surpasses anything we could dream. This is not some distant, hypothetical galaxy in a science fiction novel. This is our home, the Milky Way, and S62 is one of our own. Its journey is real. Its orbit has been mapped, measured, confirmed. It is a ghost of motion, a whisper of matter racing along the edge of non-existence. For much of human history, the core of our galaxy was a mystery. Using adaptive optics, which corrects for the blurring effects of Earth's atmosphere, they captured detailed images of stellar movements that had never been seen before. Every 10 years, it dives inward toward the black hole, surviving the encounter, and then whips back out again before repeating the cycle. The data gathered on S62 has helped refine our models of both stellar motion and the structure of black holes themselves. In 2020, it passed especially close to Sagittarius A*, reaching speeds so great that scientists were able to directly observe relativistic time dilation. The star was moving so fast and so deep into the black hole's gravitational field that time itself slowed down for it, exactly as predicted by Einstein over a century ago. What they discovered was stunning dozens of stars darting around an invisible center point, tracing paths that only made sense if something unimaginably massive and compact were pulling on them. Our telescopes, reliant on visible light, could not see through the cosmic fog. It wasn't until the development of infrared astronomy that we gained the ability to peer into the galactic heart. Infrared light can pass through dust that blocks visible wavelengths, allowing astronomers to see what lies hidden. And where one lonely star has found itself locked in an eternal dance with darkness. This star is called S62, a name as clinical as it is cosmic. A simple label given by astronomers to identify a celestial body unlike any other we have found. It is not the brightest star, nor the largest. It sits like a hidden king on a dark throne, invisible to the naked eye, yet unmistakable in its gravitational influence. And orbiting that dark monarch, like a firefly darting near the edge of a bonfire, is S62. Its orbit is a narrow ellipse, slicing through space in a 10-year cycle. At its closest point, known as pericenter, it swoops within a mere 16 billion kilometers of the black hole that is roughly 4 times the distance between our Sun and Neptune. In cosmic terms, this is breathtakingly close. And at that point, 62 accelerates to nearly 8% the speed of light, blistering 24,000 kilometers per second. It does not shimmer with vivid color or burn with spectacular intensity. But what it does is perhaps more extraordinary than all of that. It moves faster than any other known star in our galaxy. And it circles closer to the edge of oblivion than any object of its kind has ever dared. In the great galactic casino, S62 is a gambler who keeps returning to the table, brushing past destruction each time only to survive again. At the very center of the Milky Way lies an object known as Sagittarius A*, a supermassive black hole weighing more than 4 million times the mass of the Sun. To travel at that speed is to bend the very fabric of reality. But how do we even know this star exists when the galactic center is hidden behind vast clouds of dust and gas? Beginning in the 1990s and continuing into the early 2000s, teams of astronomers using the Very Large Telescope in Chile and the Keck Observatory in Hawaii began meticulously tracking the orbits of stars near Sagittarius A*. S62 was first identified during these long-term studies. It stood out immediately, not just for its high velocity, but for the extremity of its orbit. And that's not all. The precision of S62's orbit is allowing researchers to test general relativity in ways never before possible. But while these facts inspire wonder, they also invite deeper questions. Some scientists believe S62 may have once been part of a binary star system, 2 stars orbiting each other until its partner was captured or destroyed by the black hole, leaving S62 to spiral inward alone. And still, it races on. When you consider the sheer speed of S62 moving at a velocity wherein the time it takes you to blink, its story reminds us that the universe is not static or silent. As we continue through this series, we'll explore the other stars that keep company with S62 near Sagittarius A*, and it does this not once, but endlessly, as if it knows something we don't. Long before the name Sagittarius A** entered the scientific vocabulary, long before humanity even had the tools to observe the distant reaches of the cosmos, the center of the Milky Way existed as a silent enigma, hidden behind an impenetrable veil. For ancient skywatchers, the galactic core was simply the brightest, densest patch of stars visible in the summer night sky, a glowing band that stretched from horizon to horizon, wrapped around the Earth like a celestial river. They did not know they were gazing toward the most powerful object in our galaxy, a place that defies understanding and warps reality. They had no idea that deep within that light was a darkness so complete it could bend time. Even today, if you look up with your bare eyes, all you'll see is starlight. These stars, called S-stars, were not moving in random directions. That event marked the first time a star had been observed completing a full orbit around the black hole, a single circuit that took about 16 years. But S62, the star we explored in the last part, took things even further. Its orbit was tighter, its speed faster, and its trajectory even more extreme. There is no known object in the universe that could create such gravitational influence without emitting detectable light. A black hole was the only answer. And thanks to these stars, astronomers could map the mass and influence of Sagittarius A** with astonishing precision. But with data, with measurements, with light that we cannot see but can interpret, the center of the Milky Way was no longer a blank spot on the map. It was a swirling vortex of gravity, dust, and time anchored by a supermassive black hole, surrounded by a high-speed ballet of stars. They were circling a single tiny point in space, a location where no visible object could be seen. As infrared techniques improved, and as X-ray and radio telescopes added their contributions, scientists began to notice flares, brief flashes of energy near the black hole, likely caused by clumps of matter falling into the event horizon. Some are massive and young, born in a place where star formation should be impossible. Right now, the center of the galaxy glows with a light you cannot see, hiding a darkness you cannot imagine. And behind that darkness, the universe is whispering secrets, waiting for someone to learn how to listen. Others are old and compact, remnants of ancient generations. Together, they form a stellar menagerie that defies expectation and fuels new questions. These flares offered more than just spectacle. They provided timing markers that helped measure the rotation and structure of the black hole's accretion disk. Even now, we are still decoding what these flares mean, what they reveal about the strange physics operating at the edge of a singularity. After all, the galactic core is not an empty place. It is packed with stars, gas clouds, radiation, and debris. Light from these various sources overlaps and competes. And yet scientists can identify and track individual points of light with incredible accuracy. The very structure of our galaxy, including our own sun's position within it, is shaped by the gravity of Sagittarius A*. If the center of the Milky Way were different, or if its black hole were more active, our cosmic neighborhood would be drastically altered. The stability of our star, our planet, our very existence depends on a balance of forces that we are only beginning to understand. The secret lies in the power of long-term observation and pattern recognition. The extreme environments around black holes are laboratories, where our current theories break down, where Newtonian gravity fails and Einstein's equations stretch to their limits. Observing these regions gives us clues about what lies beyond general relativity, perhaps pointing toward a deeper, unified theory of gravity and quantum mechanics. The orbits were tight and fast, implying a massive gravitational source. Stars near the galactic center move rapidly due to the extreme gravitational pull. Over time, their curved orbits become visible, like time-lapse photography of planets in motion. These patterns are not random. They form ellipses. And from the shape and speed of those ellipses, scientists can deduce the mass of the object being orbited, even if it is completely invisible. Yet this source emitted no visible light, no conventional radiation. It did not shine, swallowed. The only logical conclusion was that these stars were orbiting a black hole. But the truth lies behind that light, cloaked by thick clouds of cosmic dust. For decades, astronomers were blocked by this dust-fine particles of carbon and silicates spread throughout interstellar space, capable of obscuring entire regions of the universe. Our eyes, and even early telescopes, were useless against this fog. Visible light simply can't pass through it. You could point a telescope straight toward the heart of our galaxy and see nothing but a black, blank void. And so, for much of scientific history, the center of the Milky Way remained a theoretical guess calculated from the movements of stars, but invisible to the senses. One in particular stood out, later designated Sagittarius A*. It was incredibly small for something so bright, yet its gravitational effects seemed enormous. Over the next several decades, observations improved dramatically. Instruments like the Very Large Telescope in Chile and the Keck Observatory in Hawaii were equipped with something called adaptive optics, a system that adjusts for atmospheric distortion in real time, allowing for clear, high-resolution images of the cosmos. These breakthroughs were critical because they allowed astronomers to track the motion of individual stars near the center of the galaxy. It was like trying to describe the shape of a mountain hidden behind a permanent storm. Everything changed with the rise of infrared astronomy. Infrared light, which lies just beyond the red end of the visible spectrum, has longer wavelengths that can pass through dust far more effectively than visible light. What was opaque to our eyes became transparent in the infrared. When scientists began building telescopes that could detect this form of radiation, the veil began to lift. And what they found beneath that veil was both stunning and terrifying. The first hints came in the 1970s, when infrared detectors began revealing strange, compact radio sources from the galactic center. And this is where things became extraordinary. What astronomers began to see was that dozens of stars were orbiting something invisible. In 2002, the star S2 passed incredibly close to the center, reaching speeds of around 5,000 kilometers per second. But let us pause here and ask something simple. How do we even detect these stars in such a chaotic, crowded part of space? By capturing images of the same patch of sky, night after night, year after year, astronomers can observe motion. In the case of Sagittarius A*, math pointed to a single conclusion: supermassive black hole with over 4 million solar masses, crammed into a space no larger than our solar system. And so, through indirect observation, we began to draw a portrait of the galactic center, not with brushes or photographs. Yet the discoveries did not stop there. So why does this matter? Why should we care about seeing through the dust, about mapping stars no one can visit, about finding patterns in the dark? Because these observations do more than satisfy curiosity, they help define reality. Moreover, studying the galactic center allows us to test the boundaries of physics. And so, every time we peer into that dust-filled center, every time a telescope locks onto a flicker of motion, we inch closer to understanding not just the heart of the galaxy, but the heart of nature itself. In the next part of this journey, we will explore the strange and varied group of stars that dwell near Sagittarius A*. But for now, just lie back and let this thought carry you, above you. Somewhere near the very heart of our Milky Way galaxy, in a place where gravity runs wild and time bends like soft metal, there is a strange neighborhood of stars unlike any other in the known universe. This small cluster of stars orbits impossibly close to Sagittarius A*, our galaxy's supermassive black hole. These aren't ordinary stars. They are the S-stars. And their lives, orbits, and behaviors have puzzled astronomers for decades. They twist and turn in ways that seem to ignore the normal rules of stellar dynamics. Some appear too young to exist where they are. Others move so fast they test the limits of physics. One possibility is that these stars didn't T-form near the black hole at all. They were born farther out, in the galaxy's quieter regions, and then migrated inward due to gravitational interactions. But this raises more questions. How would they migrate that far? And why would their orbits become so tightly bound? Another idea suggests that binary star systems wandered too close to the black hole. When they did, tidal forces ripped them apart. One star got flung outward at extreme speed, becoming a so-called hypervelocity star, while the other was captured by the black hole's gravity and thrown into a tight orbit. This would explain some of the orbits, but not all. Watching these processions over years and decades gives physicists one of the most sensitive tools for testing gravity under extreme conditions. But all of them tell a story, a quiet, cryptic story unfolding in the darkness at the center of everything. The environment is too harsh for the kind of planetary systems we see around calmer stars. There is no warm cradle of life here, just radiation, dust, and the constant pull of something invisible and vast. They are survivors. They endure in a place where logic says they should not exist. When you look up at the hazy stripe of the Milky Way in the night sky, you are looking toward the home of these stars, toward the place where space curves and time runs differently, toward the deepest part of our own galaxy's soul. They dance through a storm of radiation and gravity, held captive by a force that would destroy anything else. Their orbits are graceful and violent, slow and sudden, predictable and strange, and they are alone. Some astronomers propose that dense gas disks once surrounded Sagittarius A*, and that these disks were thick enough for gravity to overcome the tidal forces and collapse into stars. The S-stars don't just orbit a black hole. They orbit our understanding of how stars behave, a quiet witness to the dark, beating heart of the galaxy. Their lives offer glimpses of processes we don't yet fully grasp. In this model, the stars would have formed in situ, right where they are now, and the gas disk would have since dissipated or been absorbed by the black hole. Every wobble in their path, every flicker in their brightness, every shift in their speed, it all tells us something about gravity, about formation, about survival, about the strange, resilient persistence of matter in a place defined by its absence. Let's start by imagining what life is like that close to a supermassive black hole. When S2 made its close approach in 2018, researchers detected a phenomenon known as gravitational redshift. This means that as the star moved closer to the black hole, the light it emitted was stretched to longer wavelengths by the intense gravitational pull, just as Einstein predicted. It was a powerful confirmation of the theory in a setting where gravity is millions of times stronger than in our solar system. At the very center, Sagittarius A* sits like a sleeping titan, 4,000,000 times the mass of our Sun packed into a space smaller than Mercury's orbit. Around this invisible giant, stars circle in tight, fast loops, like moths around a flame they can never reach. The space here is dense with radiation, warped by gravity, and filled with clouds of hot gas and dust. It's not a gentle place, and yet, there they are. Dozens of stars zipping around this black hole at speeds that can reach up to 8% of the speed of light. Like the star S62, as we explored earlier. What's strange is not just how fast they move, but how young some of them are. Take S2, one of the most well-studied members of the S-star cluster. In astrophysics, young stars tend to form in calm, dense molecular clouds, where gas can cool and condense under gravity. But near Sagittarius A*, the environment is the opposite of calm. The tidal forces from the black hole are so extreme that they should tear apart any clouds that get close. So how could these stars have formed there? How did they survive? It completes a full orbit around the black hole every 16 years and at its closest. Approach comes within just 17 light hours of the event horizon, about 120 times the Earth-Sun distance. That's closer than any other known star has been to a supermassive black hole. And yet, despite living in such a hostile place, S2 is a bright, blue, relatively young star. And it's not alone. There are more than a dozen stars in this cluster that seem too young to be here. This puzzle became known as the paradox of youth. Several theories have been proposed. A third theory, more exotic, is that star formation can still occur near the black hole, but under very specific conditions. Each theory has its strengths, but none are complete. That's the nature of science at the edge of the unknown. And there's more. The orbits of these stars are incredibly precise, and watching them allows astronomers to test Einstein's general theory of relativity in the strongest gravitational field we can observe directly. The stars also exhibit orbital precession, meaning that their elliptical paths slowly rotate over time due to the curvature of space-time itself. Another relativistic effect. But beyond the math, beyond the measurements, there's something quietly poetic about these stars. No planets orbit them, at least none we can detect. Each S-star is a mystery, a messenger, and perhaps the strangest thing is this: they are not that far away. Okay. Sagittarius A* is about 26,000 light-years from Earth. That may sound immense, but in galactic terms, it's our backyard. The S-stars aren't just scientific curiosities. They're beacons. Not of light, exactly, but of knowledge. And maybe that's the most comforting thought of all. That even in the darkest, most violent corners of the universe, stars still shine. Imagine, if you will, a star caught in the grasp of something so powerful it bends time and space around it like fabric curling around a weight. Not just drawn in by gravity, but compelled into a strange, looping waltz. Pulled forward, slowed, curved, and spun. Not once, not twice, but endlessly, like a moth circling a lantern, whose flame it can never quite reach. It is bright, hot, and fast, circling Sagittarius A* in an orbit so eccentric, it plunges inward at breakneck speeds before slingshotting outward again. S2 completes a full orbit every 16 Earth years, and during its closest approach, it passes within just 17 light-hours of the black hole. To put that in perspective, that's less than 3 times the distance between Pluto and our Sun. But instead of orbiting a calm yellow star, S2 is circling a void with a mass of over 4 million suns. This is the reality of the stars near Sagittarius A*, and among them, none dance more boldly than a group known simply as the S-stars. High above us, at the very core of the Milky Way, these stars live dangerously close to the black hole at the galaxy's center. As S2 approached the black hole, the intense gravity stretched the light it emitted, shifting it to longer wavelengths. This effect had never been observed so clearly before in a star's orbit. But thanks to advanced instruments at the Very Large Telescope in Chile and the Keck Observatory in Hawaii, the measurement was made. It's confirmed, once again, that Einstein's equations hold up, even in the most extreme conditions we can observe. And during its closest approach, it moves at 24,000 kilometers per second, which is roughly 8% the speed of light. It is, as far as we know, the fastest moving star in the known universe. And it survives. Year after year. Orbit after orbit because of a delicate balance between speed and gravity, inertia and pull. They are among the most studied and also the most mysterious. By studying how they move, we can use the same physics that govern a pendulum or a planet's orbit. Newton's laws, they may have migrated inward over time, pulled gradually from larger orbits into tighter spirals. Another theory suggests they may be the survivors of more dramatic events, perhaps once part of binary star systems where one star was consumed by the black hole, while the other was slingshotted into a tight orbit. But near Sagittarius A*, the effects become measurable. The orbits of the S-stars precess, that is, their ellipses slowly rotate. Not because of planetary tugs like Mercury's orbit, but because of space-time itself bending under the black hole's mass. These could be due to unseen masses, dark matter, rogue planets, or even small black holes orbiting the big one. Or they could hint at new physics, undiscovered forces, or the need to refine our current theories. This precession has now been measured with growing precision, and it matches the predictions of relativity beautifully. These possibilities are still being studied, and each new star observed adds a clue to the puzzle. S38, S55, S62, and many others, each dance through this chaotic environment. Some complete their orbits in decades, others in mere years. Some follow tight ellipses, others wider loops. There is rhythm, there is structure. Stars do not fall in at random. They move in patterns. They obey laws. They speak a language written not in sound, but in curves and cycles. But with the right tools and the right patience, we can trace their paths. We can follow their loops and spirals. we can listen to the mathematics of their dance. And in doing so, we glimpse something ancient, precise, and deeply beautiful. They carry information in their motion, secrets written in speed, angle, distance, and light. Every data point helps us understand a little more about what gravity really is and how it behaves at the extremes. Together, they form a kind of cosmic ballet, choreographed by gravity, rehearsed over millennia. Invisible to the eye, but now slowly mapped by human hands and minds. They watch for tiny changes, track new stars, refine their models. They calculate orbits down to fractions of arcseconds. They measure shifts in spectral lines. They wait for each closest approach, each flicker of gravitational redshift, each echo of a light wave bent by a force older than time, refined by Einstein's equations, to deduce the mass of the invisible object they orbit. Over decades of observation, researchers have refined their models until we now know, with high confidence, that Sagittarius A* weighs around 4.3 million solar masses compressed into a region no larger than our solar system. Their movements have fascinated astronomers for decades, not just for their elegance, but for what they reveal about mass, time, and the shape of reality itself. The most famous of them is S2, sometimes called the Daredevil star. At its closest point, S2 races through space at more than 7,600 kilometers per second. That's over 2% the speed of light. This motion is not just impressive, it's essential, because S2 and stars like it have allowed scientists to weigh the black hole. But there is more. S2's orbit has revealed subtle warps in space itself. During its closest approach in 2018, scientists watched for something known as gravitational redshift, a prediction of Einstein's general theory of relativity. And S2 isn't alone. Other S-stars have now been tracked, each with their own unique orbital paths. But perhaps the most fascinating orbit discovered so far belongs to the star S62. This small, faint star whirls around the black hole at unprecedented speed. Its orbit is the shortest known, just 9.9 years. This strange dance raises deeper questions. Why are these stars here? How did they get so close to such a dangerous force? And how are they surviving in a place where even light can't escape? One idea is that these stars didn't form where they are. But these orbits don't just intrigue astronomers. They offer a rare laboratory for testing physics. In most parts of space, the differences between Newton's gravity and Einstein's curvature of spacetime are too subtle to detect. Still, there are mysteries. Sometimes, the orbits don't behave exactly as expected. There are slight deviations, strange wobbles, minor anomalies. In this way, the S-stars do more than just orbit. They test the universe. And so, year after year, teams of astronomers continue to observe. And we get to watch, too. We can't see these orbits with the naked eye. They're hidden behind 26,000 light-years of dust, gas, and intervening stars. Because in the end, these orbits remind us of something profound. Even in the most chaotic places in the universe, near black holes, in the heart of galaxies where light dies and gravity reigns, there is order. And perhaps, by studying these orbits, we're not just learning about black holes. We're learning about the architecture of reality itself. What holds things together? What keeps the stars in place? What keeps us here? If the galaxy were a grand ballroom, then Sagittarius A* would be the silent figure in the center of the floor, surrounded by a crowd of swirling dancers. Stars, gas, dust, all moving to the invisible rhythm of gravity. But not every star in that ballroom leaves the dance unharmed. Some venture too close. And when they do, what happens next is both horrifying and beautiful. And if it sounds gentle, like the ocean pulling on the shore, Dan T. be fooled. What we really talking about is a process that shreds a star into glowing ribbons of plasma and then swirls it into an accretion disk of pure violence. Let us talk about the tidal deaths of stars. Cosmic tragedies that occur when a star wanders too near a supermassive black hole, their influence is differential, meaning they pull harder on the parts of an object that are closer. This is the tidal force. The side of the star closest to the black hole feels a stronger gravitational pull than the far side. As the star drifts closer, that difference becomes more extreme and is torn apart by a force so powerful that even light struggles to escape. It's taken millions of years to arrive here, perhaps nudged by the gravitational influence of another passing object. As it draws nearer to the center, Sagittarius A** becomes the dominant presence in its sky, not visually, but gravitationally. It's not an explosion like a supernova, but a disassembly, a slow unweaving of matter by invisible fingers of force. The black hole, though invisible, begins to tug at the star with increasing strength. The technical name for this event is a tidal disruption event, or TDE. This flare can outshine every other source in the galaxy for days or even weeks. From Earth, it's like watching a match flare in a pitch-dark forest. Sudden, shocking, and brief. But let's slow it down and step through what happens. Piece by piece. Imagine a star, say one like our Sun, drifting through the inner core of the Milky Way. Have we actually seen it happen? Now, black holes don't just pull like magnets. First, the star stretches. Then it begins to deform. The beautiful sphere of plasma becomes a teardrop, an elongated shape pulled forward by gravity, but held together by its own fusion-fueled integrity. In each case, the signature is distinct, a brightening that follows a predictable curve, with a rapid rise and a slower decline, matching the models we've built to understand how stars die in the grip of black holes. Some of it forms loops and arcs, falling back months or even years later. This fallback material can cause secondary flares, echoes of the original event. We only see the light shifted across space, stretched by expansion, arriving years or centuries after it occurred. But that's the beauty of astronomy. We're not just watching distant places, because our instruments are trained on the center of the Milky Way. Astronomers are constantly scanning for changes, signs of flickering, of movement, of something brightening unexpectedly. But there comes a point called the Roche limit, where the tidal forces exceed the star's ability to hold itself together. NASA called the event ASA SSN19BT, and it was among the first to be caught early in its progression. Instruments picked up the telltale rise in ultraviolet light, followed by a cooling curve as the shredded matter spiraled in. Many thought it might be tidally disrupted, creating a flare. But G2 survived. Barely, and its interaction gave us insight into the density and structure of the accretion region around Sagittarius A*, and that's when things break apart. In a span of hours, the star is torn into strands. Long, fiery filaments of hydrogen and helium stripped from the core and pulled into spiraling arcs. We know our galactic center has likely consumed stars in the past. The infrared environment around it is littered with fast-moving objects, including dust clouds and smaller stars. Every so often, one ventures too close. About half of the star's mass is flung outward, back into the galaxy. But the other half, the unlucky half, is pulled inward, captured by the black hole's immense gravity and drawn toward the event horizon. As this debris falls, it forms a temporary accretion disk, a spinning ring of ultra-hot material glowing in ultraviolet and X-ray light. And then it fades. It's alive, with forces pulling, breaking, reforming. A place where stars can live for billions of years, only to be unmade in a single orbit gone too close. The star is gone. The black hole is unchanged. Pulled just a little too far, its atoms screaming across the sky, its death lighting up a corner of the galaxy for just a moment. But for a short time, we saw it, the echo of a star's final moments. Now, you might wonder, how do we know all this? The answer is yes. But in a universe filled with billions of galaxies, they occur all the time, each one an unwitnessed death or a captured moment of cosmic hunger. Over the last 2 decades, astronomers have observed dozens of confirmed TDEs. Some were detected by their X-ray emissions, others by optical flares or radio afterglows. One such event occurred in 2019, when a star, roughly the size of our Sun, wandered too close to a black hole located 375 million light-years away. It wasn't just a light show. It was a story, unfolding in real time across the cosmos. And although that black hole wasn't Sagittarius A*, the physics are the same. And when it does, the ballet ends in tragedy. Now, here's something even more fascinating. When a star is tidally disrupted, the debris doesn't fall in all at once. Some of it slows down. So even after the death of the star, its remnants continue to feed the black hole, slowly spiraling inward like ghostly echoes of its former self. From our perspective on Earth, the entire event plays out in extreme slow motion. We're watching distant times. Now, let's return to Sagittarius A*, and imagine this event happening in our own galactic neighborhood. In 2011, something curious appeared. A gas cloud called G2, hurtling toward the black hole at high speed. But one day, it won't be a gas cloud. One day, it will be a star. And when that happens, we'll watch and listen and learn. Because every tidal disruption is a message, a story written in light, whispered across space by gravity's invisible hand. It tells us not just about destruction, but about structure, how black holes feed, how they grow, how they shape the galaxies around them. And for a moment, it reminds us that even the most powerful forces in the universe can only act when something comes close. Otherwise, they remain quiet, dormant, watching, waiting. And that brings us to a final thought. Tidal disruption events are rare on human timescales. In a galaxy the size of the Milky Way, one might happen every 10,000 to 100,000 years. And the more we watch, the more we realize the universe isn't still. So the next time you look up at the night sky, try to imagine it. A star at the edge of safety, gone, but not forgotten. Just another dance partner lost in the arms of Sagittarius. Imagine standing on a rocky outcrop on the surface of a distant planet, watching the sky curve and shimmer around you. In the distance, a colossal black sphere hangs suspended in the heavens, so dark, so perfectly black, that it seems to swallow even your thoughts. That's the black hole. It doesn't shimmer, it doesn't flicker, it simply is. A silence in the sky, an absence of everything, and yet a presence unlike anything else. You check your watch, then you check the time again. Nothing seems wrong, but you feel it in your bones, in the strange tension of the world around you. Because here, near this immense mass, time doesn't behave the way you remember. It slows down. Welcome to the strange world of relativistic time dilation, a concept predicted by Einstein over a century ago. Proven by countless experiments and experienced in the most extreme form near black holes. This is not fiction. This is reality. When gravity grows strong enough, it bends time itself. To understand this, we need to go back to a fundamental truth about the universe. According to Einstein's theory of general relativity, gravity is not just a force, it's a warping of space and time. Massive objects like stars and planets bend the fabric of the universe around them. But the more massive the object, the more dramatic the bend. And when that object is a black hole, especially a supermassive black hole, like Sagittarius A*, the bending becomes so extreme that time slows dramatically in its vicinity. This isn't metaphorical. It's measurable. If you could hover just outside the event horizon of Sagittarius A*, a single minute for you might equate to hours, days, or even years for someone far away. Like on Earth, from your perspective, everything out in the galaxy would seem to be moving in fast forward. Stars spinning like whirlpools, galaxies shifting like storm clouds. But for you, in the grip of gravity's slow breath, time would move like molasses. Tick, dot, dot. Tick, dot, dot. Tick, dot, dot. Tick, dot, dot. Each second dragging behind it the weight of entire seasons elsewhere. And if you drifted just a little closer, time might stop altogether, frozen in place at the event horizon. From the outside, it would appear that you never quite crossed over this paradox where an outside observer sees time slowing to a halt as you approach the event horizon, while your own experience continues normally, is at the heart of what makes black holes so mysterious. Time itself becomes relative, slippery, untrustworthy. But let's take a step back and make this even clearer. We already experience mild versions of time dilation right here on Earth. In fact, GPS satellites orbiting above the planet must account for both special relativity due to their speed and general relativity due to weaker gravity to maintain precise time. Without adjusting for these effects, your GPS would be off by kilometers in just a day, in essence. The clocks on those satellites tick ever so slightly faster than clocks down here on Earth, because we're closer to Earth's mass, and therefore deeper in its gravitational well. Our time moves just a little slower. Now imagine that effect, but multiplied by millions. That's what happens near a black hole. Time dilation becomes so extreme that the concept of now starts to break down. What does it mean to share a present moment with someone far away if your seconds are their days? And what happens to causality, to communication, to understanding when even time can't be agreed upon? Here's where things get truly eerie. Let's say an astronaut flies near Sagittarius A*, spending an hour in close orbit, carefully avoiding the event horizon, but staying in the region of maximum time distortion. When they return to Earth, they discover that years have passed. Friends have grown older. Technologies have changed. History has moved on. But for them, only an hour is gone. This is not just a story idea. This is a real possibility. A consequence of the laws of physics as we currently understand them. We ever master travel to the galactic center and survive. The tidal force is there. We could use black holes as natural time machines, not to visit the past, but to skip forward, moving through time faster than everyone else. Of course, there's a cost. The closer you get to the black hole, the more you're pulled in, not just physically, but temporally. It's not just that you're moving through time at a different rate. It's that time itself begins to lose meaning near the edge. Some physicists have described the event horizon as a one-way membrane in time. Once you cross it, not only can you not return, you can't even send a signal back. From the outside, your fall appears to freeze at the edge. But for you, inside, the universe compresses into a final heartbeat of light. And then, nothing, no one knows what happens next. But before we go that far, let's return to the safety of imagination. Picture yourself on a ship orbiting just beyond the danger zone. The instruments on board are constantly sending telemetry back to mission control on Earth. At first, everything is in sync, but gradually, the signals begin to slow. Earth receives fewer updates. It's as if the ship is drifting into a molasses of time. Eventually, the last message is received, not because the ship was destroyed, but because the flow of time itself has slowed beyond our ability to interact with it. The ship continues, but from our point of view, it has vanished. This boundary, this temporal horizon, challenges our understanding of reality. It suggests that what we perceive as permanent or shared may actually be deeply individual, shaped by where we are and how much gravity surrounds us. It also means that time travel, in a sense, is not only real, it's happening all the time, not in machines or portals, but in nature. Right now, at the edge of Sagittarius A*, time is moving differently than it is here. Right now, a photon could be circling the black hole's edge in a tight loop, trapped in a gravitational ballet that we can only model with equations. Right now, a star might be skimming close enough to stretch its own seconds into decades for. As in right now, we're discovering that our deepest assumptions that clocks tick the same everywhere. That moments are universal, are illusions created. By living in a gentle corner of the cosmos, the truth is stranger and far more beautiful, because if time can bend, then so can everything we understand about motion, cause, and memory. In some sense, black holes are mirrors that reflect not what we are, but what we misunderstand about the world. They show us that space is not flat, time is not absolute, and reality is far more flexible than we've ever imagined. And so we return to Sagittarius A*, not just as a monster in the dark, but as a laboratory of truth. A place where physics breaks open and shows us its raw inner machinery, every orbit around that shadow is a spiral through warped time. Every pulse of radiation is a tick on a clock that doesn't match our own, and every attempt to study it brings us closer, not just to understanding the black hole, but to understanding ourselves as creatures bound by time and yet forever trying to peek beyond its edge. So as you lie back, letting your thoughts drift like stardust across the dark canvas of space, remember this: time is not a river, it's a landscape, and black holes are the deep valleys in that land, places where seconds stretch and minutes vanish, and the universe whispers its oldest secrets in the silence between ticks. In the next part of this series, we'll explore the echoes of light, how the emissions from Sagittarius A reveal the structure of its hidden heart, and how flares and flickers are decoded to create an image of the unseeable. But for now, let your thoughts slow down, let time soften, and rest in the gravity of a truth that's as strange as any dream. There's something haunting about trying to see what refuses to be seen. Like chasing shadows in a room with no light, or listening for echoes in a place where sound doesn't travel. That's what it's like when scientists try to image a black hole. Because how do you take a picture of something that doesn't let light escape? How do you photograph the one thing in the universe designed to erase its own visibility? And yet, we've done it. Not just once, but more than once now. First with the famous image of the black hole in galaxy M87, and more recently with the long-awaited glimpse of Sagittarius A*, the supermassive black hole at the heart of our own Milky Way. It wasn't easy. It wasn't quick, but it changed everything, because for the first time in human history, we looked into the darkness and saw the imprint of something no eye was ever meant to witness. So how do you take a picture of a black hole? The secret lies not in the black hole itself, but in what surrounds it. You see? Even though the event horizon of a black hole is invisible, the space around it is anything but. Matter that falls toward a black hole doesn't fall in silently. It spirals, compresses, and heats to unimaginable temperatures, glowing fiercely in X-rays and radio waves. This swirling disk of glowing gas is called the accretion disk, and it's often brighter than entire galaxies. But around Sagittarius A*, that glow is not constant. It flickers, it flares. It pulses in brief, chaotic flashes that last just minutes or hours. Astronomers call these light echoes, short bursts of radiation that illuminates a space round the black hole before fading into darkness again. And by tracking these echoes across time, scientists can piece together an image not of the black hole itself, but of the space warped around it. This is how we see the UNSEEA. It's like mapping a cave not by looking inside, but by throwing balls that bounce off the walls and listening for the sound. But here, the balls are photons, and the sound is light warped by gravity. To capture the image of Sagittarius A*, scientists needed a telescope the size of Earth itself. That's not an exaggeration. The black hole shadow is so small in the sky, like seeing a donut on the moon from Earth, that no single telescope could possibly resolve it. So they created one. They link together 8 radio telescopes around the world. From Hawaii to Chile to the South Pole, forming a network called the Event Horizon Telescope, or EHT. It works using a technique called Very Long Baseline interferometry, a method that synchronizes distant telescopes with atomic clocks, allowing them to function as if they were parts of a single, planet-sized dish. And in April 2017, they pointed them all at Sagittarius A*. What came next was not immediate. The data was massive petabytes of information. It's too large to transmit over the internet. So scientists shipped hard drives to a central processing location where supercomputers began the painstaking work of combining the data. But the biggest challenge wasn't the size. It was the chaos. You see, Sagittarius A* is an unusually quiet black hole. It doesn't consume much matter, and what it does eat, it eats in unpredictable bursts. That meant the image was constantly shifting, flickering like a candle in wind. Unlike the black hole in M87, which was relatively stable, Sagittarius A* pulsed in real time. Imagine trying to photograph something that changes shape every few minutes, and yet, they did it after years of analysis, modeling, and validation. The team released the first ever image of Sagittarius A* in 2022. A glowing ring, a shadow at the center, and confirmation that Einstein's equations still held true even here, on the edge of everything. But the image wasn't just a triumph of physics. It was a triumph of patience, of imagination, of faith in the power of collaboration. Over 300 scientists from around the globe worked together to reveal this portrait. A blurry ring of fire surrounding a hole that isn't a hole, but rather a boundary beyond which we cannot return. The ring we see isn't the black hole itself, but rather the light bent by gravity around it, a phenomenon called the photon sphere. Photons, light particles that venture too close to the event horizon, don't always fall in. Some of them skim the edge, caught in circular orbits by gravity so strong that light itself loops endlessly before escaping in the direction of Earth. That glowing ring is light that has traveled in impossible paths. Some of the photons we see in that image have looped around the black hole more than once before reaching our telescopes. That's what we mean when we say we're seeing into the past. The ring is a fossil record of LIGHT. Memory? A cosmic whisper from a region where time and space fold like cloth in the hand of an invisible giant. But even now, we're just beginning to understand what this image truly means. Because with each flicker, with each variation in brightness, Sagittarius A* is telling us something about its spin, about the turbulence of its surrounding plasma, about the subtle warping of spacetime around its edges. And through this dance of echoes, we learn, we simulate, we create models that predict how light behaves under extreme conditions. And we compare those models to the real data, testing not just our ideas about black holes, but about the very nature of reality. What does it mean that light can orbit, that time can stretch? That information, once consumed, may not be lost forever, but scrambled, encoded, hidden in ways we have yet to understand. These questions aren't science fiction. They're the frontier of modern astrophysics, and they begin here with a glowing ring in the sky captured by a telescope made of continents. The next step, we go deeper. In future missions, astronomers hope to launch radio telescopes into orbit, creating a space-based event horizon telescope with even greater resolution. With it, we could watch the black hole's shadow in real time, see how it shifts, pulses, breathes. We might one day watch matter fall in, we might glimpse magnetic storms. The size of planets, we might, just maybe, see something that changes everything. Because light carries more than illumination. It carries memory, it carries structure, and even in the darkest places, it leaves traces of the truth. So as you lie in the quiet of the night, imagining the heart of the galaxy turning in silence, remember this: we are not blind to the darkness. We are learning to see in ways our ancestors never dreamed possible. Through patience, through science, through light that dares to orbit the abyss. And even if the shadows are deep, we are not without lanterns, because every flicker from Sagittarius A** is a message, a note in the bottle of space-time, drifting across the void, waiting to be read, and we are reading it together. Let your thoughts drift now into that quiet ring of light. Let the mysteries of the universe settle around you like a blanket of stars, and rest in the comfort of knowing that even the darkest places leave reflections. Even silence has a shape. Even shadows can teach us to see. Imagine a door that opens only one way. A threshold that can be crossed but never recrossed. A place where light, time, and memory all reach a boundary and vanish. That's the event horizon, the surface of a black hole, the point of no return. But what lies beyond it? No one knows, not for certain. Not yet. It's the ultimate cosmic mystery, not just because it's hidden, but because it might be unknowable by the rules we currently understand. Beyond the event horizon, physics as we know it begins to break down. Space and time switch roles. Gravity becomes dominant beyond measure, and even the concept of inside begins to lose its meaning. Still, we try to imagine, and with that imagination, guided by equations and theory, we've begun to sketch the outlines of a realm that defies reality itself. Let's begin with what we do know. A black hole forms when matter collapses under its own gravity to a single point, a singularity, where density becomes infinite. It's not just crushed, it's erased from the geometry of space itself. According to Einstein's general relativity, this singularity lies at the center of the black hole, hidden forever behind the event horizon. If you were to fall toward the event horizon, your experience would depend on the size of the black hole. For a small stellar mass black hole, tidal forces would stretch your body like spaghetti, a process known as spaghettification, long before you ever reach the horizon. But if the black hole were supermassive, like Sagittarius A**, those same tidal forces might be weak enough to let you pass the horizon unharmed. For a time, you would fall weightless, feeling nothing unusual at first. You wouldn't see a sign that says, "Now leaving reality." The outside universe would seem to speed up as you fell, the stars racing in fast forward. You'd cross the event horizon silently, with no flash, no sound, and once you did, nothing could ever carry your information back, not even light, not even time. Inside the horizon, every path forward leads not to the future, but inward, toward the singularity, a place where the known laws of the universe break apart. But what if the singularity isn't the end? Some scientists believe it might not be a point at all, but a gateway, a portal to a different universe, a bridge to another region of space-time, a structure known in theory as a wormhole. A wormhole is a hypothetical tunnel connecting to separate points in space and time, like folding a piece of paper and poking a hole through it. In this idea, a black hole might be one end of such a tunnel, and on the other side, a white hole, a mirror object that expels matter instead of drawing it in. White holes have never been observed. They remain purely theoretical. But in the mathematics of general relativity, they are possible. And if they exist, they might explain how information could one day escape the grasp of a black hole, not by returning to our universe, but by emerging somewhere else entirely. Of course, this opens 1,000 other questions. Where would that somewhere else be? Another part of our own universe, a parallel reality, a past or future timeline. And what would you find there? Some theorists suggest the interior of a black hole could contain a bubble of space-time entirely cut off from ours. A baby universe forming a new cosmos birthed inside the womb of gravity itself. In this picture, every black hole might be a cosmic seed, a hidden origin, a creator of other realities. It's speculative, yes, but not impossible. There are equations that describe this. models that simulate the structure of space-time under extreme curvature. In some of them, the singularity doesn't destroy information, it compresses and transforms it, shielding it in a new realm beyond detection. But there's a catch. These theories depend on a unification of gravity and quantum mechanics, a theory of quantum gravity, which we don't yet possess. General relativity and quantum physics are the two pillars of modern science, but they don't play well together at the scales inside a black hole. One describes the cosmos at large, the other, the world of the very small, and at the singularity. These worlds collide. That's why many believe the interior of a black hole will remain a mystery until we can reconcile these theories. Until then, it's like trying to read a book where half the language hasn't been invented yet, but new insights are emerging. From string theory, we learn that particles may not be point-like, but extended vibrating strings of energy. And in this framework, black holes may have structure far richer than we thought. From loop quantum gravity, we get the idea that space-time itself may be quantized, not smooth, but made of discrete units. If true, then perhaps the singularity never becomes truly infinite, but instead reaches a maximum density, where space-time bounces instead of breaking. This leads to a radical idea, that the Big Bang itself may have emerged from the interior of a black hole, a collapse followed by a rebound, a previous universe dying and giving birth to this one. Again, speculative, but supported by math that fits what we observe. Still, the interior of a black hole doesn't just challenge our physics. It challenges our intuition, our sense of cause and effect, our belief in beginnings and endings. Inside the event horizon, time and space reverse roles. The direction you move in space becomes fixed. The singularity lies not in front of you like a place, but ahead of you like a moment in time. You cannot stop. You cannot turn. You will reach the singularity just as surely as tomorrow becomes today. What happens to you there? That depends on the theory. Some say your body and the information it contains is lost forever, that the laws of thermodynamics are violated and the universe becomes a little less ordered. Others say no, that information is preserved, not inside the black hole, but encoded on its surface, the event horizon. Like a hologram, this is the holographic principle. It says that everything that falls into a black hole might be recorded on its boundary, like a movie played backwards, ensuring that nothing is truly lost. If true, then perhaps the interior is not what it seems. Perhaps what's inside is just a projection, a mathematical reflection of the surface. But if it is more than that, there's truly a realm beyond the veil, then we are dealing with something far beyond science. We are dealing with the architecture of the cosmos. The inside of a black hole might be the closest thing we have to a forbidden chamber, a place where time dies, space folds, and cause itself collapses into mystery. It's the final metaphor, the last lighthouse before the void, and yet, even here, we are reaching, with telescopes, with math, with dreams. So the next time you hear that black holes are nothing, remember this: they are not empty, they are not simple, they are not gone. They are more, and somewhere deep inside, beyond the light, beyond the edge, something waits, a truth we are not ready to see. A chapter in the story of the universe that has not yet been opened, but one day it will be. And when it is, the question will not be what lies inside a black hole, but rather what lies beyond our imagination. Let yourself drift now. Let the horizon dissolve into thought. Let your mind fall gently past the edges of space and into the unknown. There's no fear here, only silence, only wonder, and the gentle pull of something greater than ourselves. Time is supposed to be simple. We wake up, we live our day, we sleep. Seconds turn into minutes, minutes into hours, days into years. We move forward, always forward, and never back. But what if that was only true on the surface? What if time isn't a straight road, but a landscape, something curved, warped, and twisted by the invisible hand of gravity? What if the ticking of a clock isn't constant at all, but depends entirely on where you are in the universe? Tonight, we're going to unravel one of the strangest ideas in physics: how black holes distort not just space, but time itself. So deeply that two people only meters apart might experience reality at completely different speeds. So deeply that time can slow down, stretch, and even stop. Entirely to understand this, we have to go back to Einstein. More than a century ago, he showed us that time and space aren't separate things. They're two parts of one fabric, space-time. And just like fabric, space-time can bend. When mass or energy is present, a planet, a star, or something more extreme, space-time curves around it, and where space curves, so does time. This is the essence of gravitational time dilation. The stronger the gravity, the slower time flows. You experience this every day, just slightly. Clocks on airplanes tick faster than clocks on the ground. Satellites must adjust their internal time to match ours. Astronauts age a tiny bit slower aboard the International Space Station than they would here on Earth. But these effects are minuscule, nanoseconds at most. When gravity gets stronger, however much stronger, those differences become enormous. Enter the black hole. Around a black hole, gravity is so intense that time itself begins to deform. The closer you get to the event horizon, the black hole's boundary, the more time slows down for you compared to someone far away. Imagine this. You and a friend approach a black hole. Your friend stays at a safe distance, floating far from danger. You, on the other hand, decide to move closer. As you drift toward the event horizon, your friend sees your motion slow down, slower and slower. And eventually, right as you reach the edge, you appear from your friend's perspective to freeze. Your final image becomes locked in time, motionless, forever hovering at the boundary. But to you, nothing feels strange. You keep falling, cross the horizon, drift toward the singularity. For you, time flows normally. It's not magic. It's relativity to observers. Two wildly different perceptions of the same moment. Now, let's flip it. Suppose you remain near the horizon for a few hours, shielded from the worst of the gravitational forces. When you return to your friend's ship, you discover that days, months, or even years have passed for them depending on how close you got. This isn't science fiction. It's a real, tested phenomenon. We saw it dramatized in Interstellar when the crew lands on a planet, orbiting close to a supermassive black hole. Every hour on the surface equals 7 years in space. That's not a plot device. That's physics. Black holes are time machines, but only one way. You can travel to the future faster than everyone else, but you can't go back. And this leads to the greatest paradox of all. What is time, really? Is it a flowing river, sweeping us along like leaves on the surface? Or is it more like a block, a frozen structure, where all moments exist at once, and we only perceive motion as a trick of consciousness? Physicists argue about this. Some believe in the block universe, a model where the past, present, and future all coexist. Others argue that time is emergent, a byproduct of entropy and quantum information. Black holes challenge both views. Let's go deeper, inside the event horizon. Something remarkable happens. Space and time switch roles. Time becomes a direction you must move, not forward, but inward. Every step, every moment pulls you closer to the singularity, not as a destination in space, but as a moment in time. You can't escape. You can't delay. Falling into the center becomes your future. It's not optional. It's written into the geometry of the universe. And yet, for an outside observer, you never reach it. You freeze on the edge forever. They never see your fall complete. You disappear from the universe slowly, asymptotically, as if swallowed by time itself. This duality of motion and stillness, of timelessness and collapse, is at the heart of black hole paradoxes. Now think of this. What happens to information? Suppose you fall in carrying a journal, a memory, a secret. Does that information vanish forever? If it does, then a fundamental rule of physics is broken, the conservation of information, that leads to the infamous black hole information paradox. Some scientists believe the information is lost. Others say it must be preserved somehow, encoded on the event horizon, smeared across the boundary like a cosmic tattoo. This brings us to Hawking radiation. Stephen Hawking showed that black holes aren't entirely black. They emit faint particles slowly evaporating over time. As the black hole loses mass, it shrinks. And eventually, after trillions of years, it may vanish entirely. But then what? The black hole disappears, and the information inside it was not preserved. Then the universe loses something. A piece of the puzzle goes missing. The timeline gets blurry. This is not acceptable to most physicists. Quantum mechanics demands that information be conserved always. And so we are left with an impossible choice. Either quantum theory is incomplete, or black holes are more than they seem. Some believe the answer lies in a deeper theory, one that unites quantum mechanics and gravity. A quantum theory of space-time. Others point to the holographic principle, the idea that all the information inside a region of quantum space can be described by data on its surface. In this view, the interior of the black hole is an illusion, a projection like a hologram. Time and space emerge from deeper rules we barely understand. All of this leads us to a startling conclusion. Time is not fundamental. It is not universal. It may not even be real. What we call time might just be a measure of change, an artifact of how we move through information. And black holes, they are the cracks in that illusion where the rules of time get rewritten. So, the next time you look up at the stars and imagine a black hole in the distance, remember, it's not just a place, it's a clock. A distorted, broken, melting clock where time is stretched thin, folded inward, and sealed away. It is a place where cause and effect start to crumble, where a moment can last forever, where the past, present, and future blur into a single dark truth. That time is not what we thought it was. Let your thoughts drift into that horizon now. Let time slow down like syrup across a cold plate. Feel. The seconds stretch, the hours dissolve. You're safe here, floating in the mystery, carried forward by something older than time itself. When something falls into a black hole, a spaceship, a star, a planet, even light itself, where does it actually go? That question sounds simple, almost childish, like something you'd whisper to the night sky on a sleepless evening. But, in truth, it is one of the deepest, most haunting mysteries in all of physics. Because black holes don't just destroy things, they erase. They consume. They take the matter and the information inside it and pull it past a boundary we cannot observe the event horizon into a darkness we do not understand. So tonight, we ask a question the universe still refuses to answer clearly. Where does the matter go? To begin, we must first retrace the final journey of anything that ventures too close. Let's imagine an object, a probe. It's a tiny camera, something built to survive extreme conditions. It drifts slowly toward the edge of a black hole. From the outside, we watch it get closer, slower, and then something strange happens. From our perspective, it never quite crosses the horizon. It hovers, frozen in time, as the light it emits gets stretched redder and redder until it fades into invisibility. But for the probe itself, time hasn't stopped. It crosses the event horizon in finite time, seconds, minutes, not centuries. It falls toward the center. Toward what lies within. And that's where our understanding falters, because we don't know what lies at the center of a black hole. Our best theory tells us there is a singularity, a point of infinite density and zero volume, where gravity becomes infinite and the known laws of physics break down. But infinities in physics usually mean we're missing something. They're not answers, they're warnings. Clues that the theory we're using isn't complete. So instead of assuming everything falls into a singularity and simply ends, let's explore what might actually happen to matter inside a black hole. One possibility is that everything is compressed into an unimaginably small point, not destroyed, but trapped, forever locked beyond the event horizon, unable to escape. But this leads to a problem. If the black hole later evaporates as Stephen Hawking predicted they do, through slow emission of particles called Hawking radiation, then what happens to the matter it swallowed? Does it vanish too? If so, then information is lost, permanently deleted from the universe. And that, according to quantum mechanics, is not supposed to happen. Every interaction, every decay, every transformation of matter in the universe must preserve the information within it, the quantum fingerprints of what came before. So the question becomes even sharper. Not just where does the matter go, but how can the universe preserve the information of what fell in? And from this question, several incredible ideas have emerged. One is the holographic principle. The idea that all the information contained inside a black hole is somehow encoded on its surface, the event horizon itself, like a cosmic hard drive. The black hole's outer shell may store every bit of information about what has fallen inside. Even if the matter can never escape, the information about it might never be lost. In this view, the black hole becomes a kind of hologram, with the interior being a projection of data held at the boundary. Another theory proposes that information escapes during evaporation, that Hawking radiation somehow carries it out in a scrambled form. At first, this seemed impossible. Hawking's original work suggested the radiation was purely random. But in recent years, new models have shown how, in theory, quantum correlations might allow information to gradually leak back out as the black hole evaporates. This is known as the Page curve, a model that predicts how the entropy of a black hole evolves over time. If information is preserved, but none of these models can yet be tested. We've never observed Hawking radiation. We've never watched a black hole evaporate. We've never looked past the event horizon, and maybe we never will. Which leads to another possibility, that black holes don't just trap matter. They lead somewhere else entirely. Could it be that the matter falling into a black hole is not destroyed, not stored, but transported to another region of space, to another universe, to another time? Some theorists have suggested that the center of a black hole might connect to a white hole, a hypothetical object that does the opposite of a black hole. It expels matter, instead of swallowing it. In this model, black holes might be gateways, one-way tunnels, wormholes perhaps, leading to distant points in space-time. A star collapses here, and its matter explodes out there. This would preserve both the matter and the information, just not in our universe. But this idea, while beautiful, is also speculative. There is no evidence yet of white holes. Some scientists believe they may never form. Others think they could exist in the earliest moments after a black hole forms, like a brief flash of matter being thrown out before the hole settles into silence. Still others propose that information might be preserved in the geometry of space-time itself, in patterns we cannot see or measure yet. There's even an idea that black holes don't destroy information because they're actually quantum computers processing the data of everything they consume and releasing that information slowly. through complex, non-random radiation. And now, we arrive at one of the most provocative ideas in modern physics. What if nothing really goes anywhere? What if the inside of a black hole isn't a place at all, but a state? A phase of information scrambled, locked, encoded, but still existing. This leads us to firewalls. The controversial idea that the boundary of a black hole might be a seething high-energy wall that burns anything falling in, if true. This would shatter general relativity's prediction of a smooth event horizon. It would mean that black holes aren't the silent monsters we thought, but violent places, where information is preserved in the most brutal way possible. But again, we don't know. The problem isn't that black holes hide their answers. It's that they destroy our ability to ask the question. We cannot look inside. We cannot test our ideas. And so we are left with echoes, equations, and imagination. And that brings us back to the mystery. Where does the matter go? We don't know it. Might be stored on the horizon. It might be released as radiation. It might emerge somewhere else. Or it might never leave, just transformed into something beyond our understanding. And maybe that's the point. Black holes remind us that the universe still contains boundaries not just of distance or size, but of knowledge. They are the edge of understanding, the crack in the mirror of physics. The silence after the question. So as you drift into sleep, think of this. Right now, somewhere far away, stars are collapsing. Galaxies are spiraling. Matter is falling into the darkness. And the universe is whispering a riddle no one has ever solved. You are part of that mystery. You are made of atoms that once came from stars that died, perhaps not so differently. You carry inside you the same questions, the same longing to know, and maybe one day we will understand. Maybe we will find a way to look beyond the horizon. But for now, we dream of spirals in the dark, light pulled into silence, of places where time ends, and of the question that still waits for its answer. Where does the matter go? Sleep well, traveler.